Hello, 7th graders. Today we are starting Chapter 13, which is basically just an extension of Chapter 12. In Chapter 12, we were looking at experimental probability, and now we'll be looking at theoretical probability. So when we're using probability, we express it as a fraction, percent, or decimal. So remembering how to convert fractions and decimals and add and subtract with them and even multiply is going to be really important. So let's check out this first section. It says write each fraction as a decimal and a percent. Okay, so remember that this fraction bar is technically a division symbol. So 3/4 is the same thing as 3 divided by 4. Now you may know what this decimal already is, or you can enter it into a calculator, do 3 divided by 4, and you will get 0.75. So that's our fraction as a decimal. Then we're going to convert that decimal to a percent. To make a decimal a percent, we take the decimal, we move it over 2 places, or we multiply by 100. So that's the same thing as 75%. All right, so this next one, we would do 2 divided by 5 in a calculator, and we'll get 0.4. Now when we move that decimal 2 places over to make a percent, we need an extra place. So I'm going to put a 0 there to be our placeholder. And that's the same thing as 40%. So 2/5 equals 0.4, which equals 40%. All right, 9/10. Well, hopefully we know this as a decimal because the decimal is actually said as 9/10, 0.9, which is the same thing as 90%. All right, I want you to pause the video, try numbers 5, 6, and 8. 5, 6, and 8, and then play it back to see if you got them right. All right, so 7/8, we do 7 divided by 8 in a calculator, and we get 0.875. If we move the decimal 2 places over, we actually get 87.5%. Make sure that's not 875%. 0.875 is less than 1, so my percent should be less than 100%. Remember, while we're talking fractions and decimals, 1 over 1 equals 1.0, which equals 100%. Those are our 1/2. So for probability, if an event is for sure going to happen, we use those 3 numbers to describe it. All right, 1/20th, I'm going to enter 1 divided by 20 into a calculator, and I get 0.05, which is 5%. And then for number 8, remember percents are actually fractions over 100. So I could do this one without a calculator because I know 50 multiplies to 100 twice. So if I multiply 23 times 2, I'm going to get a fraction over 100. So I have 46 over 100, which is also written as 46 hundredths or 46%. All right, I also want us to do a couple of these subtracting fractions from 1. It's important to remember that 1 is equal to, if you have 5 as a denominator, it's equal to 5 over 5, which is also equal to 6 over 6, or 7 over 7. Hopefully you see a pattern. Any number divided by itself is equal to 1. So instead of this 1 here, I could pretend that that 1 is 5/5. Now I have 5/5 minus 1/5. That's equal to 4/5. Number 10, we're dealing with ninths, so I'm going to pretend that 1 is 9/9. 9 minus 2 is 7, so 9/9 minus 2/9 is 7/9. All right, try numbers 11 and 12 on your own. Play the video to see if you got them right. All right, so we're going to pretend this one is 13/13. 13 minus 8 is 5. So 5/13, and then we're going to pretend this is 20/20. 20 minus 3 is 17, so that's 17/20. All right, for the sake of time, we're going to skip this bottom part. But remember, when we multiply fractions, we multiply straight across. So just number 14, random example, we would do 2 times 3 is 6, 9 times 4 is 36, and then you always simplify. Both of those are divisible by 6, so that would be equal to 1/6. So when we multiply fractions, we multiply straight across. All right, notice this box at the bottom with 3 vocab words in it. Those are some vocab words we learned in chapter 12 that are pretty important in chapter 13 as well. So probability is the likeliness that an event will occur. An event is a set of one or more outcomes. And then a trial is each observation of an experiment. Now in chapter 13, we're dealing with theoretical probability, so we won't see as many trials, but we will still see events. And in chapter 13, we have a couple more words that are important. A compound event is an event made of 2 or more simple events. Theoretical probability is the ratio of number equally likely outcomes in an event to the total number of possible outcomes. So we're going to see this ratio later. And last word I want to talk about right now is a complement. A complement is the set of all outcomes that are not the desired event. So this is why we were practicing with 1 minus fractions, because 1 minus the probability of the event is equal to the complement, or the probability that it doesn't happen. All right, so those 5 words are pretty important. Ooh, 6 words. And then there's one more. A simple event up here is an event with only one outcome. All right, so let's actually get to theoretical probability. Theoretical probability is calculated by this square here, where it says the number of sections with stars over the total number of outcomes. All right, let's read the problem. At a school fair, you have a choice of spinning spinner A or spinner B. You win an MB3 player if the spinner lands on a section with a star in it. Which spinner should you choose if you want a better chance of winning? All right, well, it looks like they're all equal sections in the spinners, so that will help us calculate our probability. Spinner A has a total number of 8 outcomes because there are 8 sections. Spinner B, oh, this might be a while to count. Okay, I'm gonna start here. 1, 2, 3, 4, 5, 6, 7, 8 times 2 is 16. So spinner B has 16 possible outcomes. All right, then we count the number of sections with stars. Spinner A has 3 sections of stars. Spinner B has 5 sections of stars. All right, so theoretical probability is the number of outcomes that match the event. So in this case, the number of sections with stars over the total number of outcomes, assuming each outcome is equally likely. Okay, so the number of sections with stars on spinner A was 3. The number of total outcomes is 8, which means the probability of landing on a star with spinner A is 3/8. All right, then let's look at spinner B. The total number of sections with stars is 5, and there are 16 total sections, which means the probability of landing on a star with spinner B is 5/16. All right, so the ratio for spinner blank is greater than the ratio for spinner blank. Well, let's compare these fractions. 3/8 we can make into 16ths by multiplying both by 2, so that's equal to 6/16, which is greater than 5/16. So the probability for spinner A is greater than spinner B. So I should choose spinner A because I have a better chance of winning. All right, before we can begin our next example, remember theoretical probability. Probability of the event is the number of ways the event can occur over the total number of equally likely outcomes. All right, next example. A bag contains 6 red marbles and 12 blue ones. You select one marble at random from the bag. What is the probability that you select a red marble? So there's 6 red, 12 blue. We want to know the probability of selecting a red. Well, the total of number of ways that event can occur, there are 6 red marbles. So there's a total of 6 different marbles we could pull. Over the total number of equally likely outcomes, well, each marble is equally likely. We're assuming they're all the same size. So we need to figure out how many are in the bag. So 6 plus 12 is 18. That means there are 18 possible outcomes. So the probability is 6 over 18. We can simplify that to 1/3, and we could even write that as a decimal, 0.3 repeating, or 33%. All right, I want you to try this next one on your own, just number 2, and then play a video back to see if you got it right. All right, pause the video, go. Okay, you roll a number cube 1 time. What is the probability you roll a 3 or 4? Well, 3 or 4, that's 2 possible outcomes. And there are 6 sides to a number cube, so out of 6 total equally likely outcomes, which we can simplify to 1/3. You don't need both of those, but 1/3, which is again the same as 0.3 repeating, or 33%. And then let's look at number 3 together. How is the sample space for an event related to the formula for the theoretical probability? Well, remember the sample space shows all possible outcomes. So if we count each space, each outcome in the sample space, it will give us the denominator of that fraction. So we need to know the sample space, or all possible outcomes, the number of possible outcomes, to find the denominator of probability and therefore find probability. All right, so how are these things actually different? We've been dealing with experimental probability. Now we're introducing theoretical probability. Why isn't there just one probability? We're going to read through this activity and see why. Okay, so now that you've calculated theoretical probabilities, you may wonder how they compare. 6 students are performing in a talent contest. You roll a number cube to determine the order of the performances. You roll the number cube once. Complete the table of theoretical probabilities for the different outcomes. Well, there's 6 sides of a number cube, so the probability you roll a 1 is 1 over 6. The probability you roll a 2 is 1 over 6. And same for each side, because there's 6 sides, they're all the same shape, they're all equally likely. So each of those 6 boxes should have a 1/6. So if you roll 30 times, we're going to predict the number of times each number will be rolled. So if you roll 30 times, you're finding 1/6 of 30 for each of these. 30 divided by 6 is 5, so I'm going to predict I roll a 1 5 times, a 2 5 times, a 3 5 times, etc. If each of these are equally likely, theoretically, I should roll an equal number of each. Okay, so this is our theoretical probability. I'm putting a T there so we remember that's theoretical probability. The next one is going to be experimental probability. So if you have a dice, you can play along. Otherwise, I have inserted a link here to a free online dice that you can just roll a dice and get outcomes for free. So how we're going to do this, we are going to record the number of times the dice lands on a 1, 2, 3, 4, 5, or 6. So you're going to roll 30 times and just put tallies in the frequency. I'm going to pause the video and do that myself, and then we will calculate experimental probability together. All right, pause, go. All right, so I have the number of times I landed on each number. I landed on a 1 4 times, a 2 6 times, a 3 2 times, 4 7, 5 5 times, and a 6 6 times. So the experimental probability of landing on a 1 is 4 out of 30, or we could simplify to 2/15. For the sake of time and space, I'm actually not going to simplify the rest of these fractions. We'll just leave them over 30. So the probability of landing on a 2 is 6 over 30, 6/30. Probability of landing on a 3 is only 2/30. A 4 is 7/30. 5 is 5/30. And a 6 is 6/30. So notice how the experimental probability is different for each number, because each number occurred differently in the experiment. So theoretically, they all should be around 5. And they're all pretty close to 5. 3 is lacking a little bit. But they're all different because the experiment is different than what should happen is different than what actually happens.